In this video, we will look deeper into the auto features available with IDS cameras. Depending on the camera family, the auto features cover auto brightness, controlling the exposure and gain, auto white balance, affecting the color balance, autofocus, which can be used to control the focus on supporting cameras, and auto black level, a newer feature that adjusts the analog black level dynamically. The auto features are performed either on camera using the camera FPGA or ISP, or in software using the peak libraries or external third-party or custom libraries. Cameras from the X series do not have an FPGA, so any auto features are run in software, whereas the CP, FA, LE and SEs are all equipped with an FPGA and the XC with an ISP. So some or all of these auto features can run directly on the camera, or we can still choose to use the software-based processing. In general, the in-camera processing will be faster and more responsive, as data does not need to be transferred to the host PC, but is more limited due to the processing resources available on the camera. Software processing has more of a lag associated with it, but as it is running on the host PC, the algorithms used can be tailored to specific requirements. With auto brightness, the camera or software measures the brightness in the image or a defined subregion, compares this to a target value, computes any difference between the image brightness and target brightness, and then, if necessary, adjusts exposure and gain to move the brightness level towards the target value. We can configure this behavior in IDS Peak Cockpit. The histogram here shows how the pixel brightness values are distributed across the image, with darker pixels on the left and brighter pixels on the right. For auto brightness, the key settings are target brightness, percentile, and tolerance. The target brightness sets the grey value that the auto brightness algorithm is trying to achieve. If we increase the target value, the image becomes brighter. If we decrease it, the image becomes darker. And the target line on the histogram shows this desired brightness level. The percentile defines which part of the histogram is used as the reference for the brightness calculation, and is used to decide how much of the image should sit above or below the target value. We see the percentile split either side of the target line on the histogram. The percentile value is useful when the image contains very bright or very dark areas that are not important for the application, such as reflections or background regions. By adjusting the percentile, we can reduce the influence of those areas and control the brightness based more on the parts of the image we actually care about. In this example, with a lower percentile value, the shiny coin reflecting the light is the dominant area in the image against which the exposure and gain is adjusted, and all other areas in the image are darker and low contrast. By increasing the percentile value, we accept more bright pixels in the image, so the exposure and gain are adjusted up and the overall brightness of the image is higher. The tolerance value determines the speed and accuracy of the auto brightness calculation and is represented by the green bar in the histogram. A higher tolerance should produce a faster result, but may be less precise. A higher tolerance gives a more targeted brightness result, but may take longer to stabilize or may continue making small adjustments. These controls are found under the Brightness Frame Rate tab in Peak Cockpit. As previously described, depending on the camera, we can select if the auto features are processed on the camera or in software on the host PC. For the auto exposure and gain, we can do a single calculation for a controlled scene, or we can do continuous evaluation if the scene is more dynamic, such as dealing with variations in daylight in outdoor applications. With continuous auto exposure and auto gain enabled, we can see in this example, the light source first increases in intensity, and so the exposure time is automatically reduced. And then as the light source intensity reduces, first the exposure time increases, and once exposure is at its maximum, the analog gain increases to maintain the target brightness. If we want to minimize noise in the image, we can just enable the auto exposure, or if we want to maintain a short exposure time to minimize motion blur, then we can enable just the auto gain. In the case of software or host-based processing, we can also reduce the processor loading by skipping a number of frames between each calculation. At the bottom of this section, we have the configuration for how auto brightness responds to changes in the image that we saw earlier. But we can also be more targeted with a scenario where brighter or darker areas affect the auto brightness calculation by setting a region of interest in which the auto brightness is calculated. Expand the auto brightness ROI section, unlock the auto brightness ROI control, enable the ROI area display, and then click on Draw ROI. We can now draw a region that only includes the areas that we care about. In this example, we exclude the sky, which is significantly brighter in the scene, and we do not care if it saturates, as long as the area covering the cars in this scene offer the right image brightness to detect the required features. When working with color cameras, the factory settings are unlikely to provide an optimum color image for the scene, as different forms of lighting have different color temperatures, so we need different color settings depending on the light source. Here, with the line view tool in Peak Cockpit, we can see the red, green and blue levels over a neutral target, and if we had the correct white balance, these RGB values would be aligned in the line profile. In this case, we can see a bias towards red under the first two light sources. The third light source is closer, but still not optimum. To achieve a good white balance, we can use the Auto White Balance tool in Peak Cockpit, found in the Color section. When imaging a neutral white or grey scene, we can perform a one-time white balance if our scene has controlled lighting, or a continuous white balance correction for more dynamic scenes. The Auto White Balance algorithm evaluates the scene and adjusts the RGB color gain values so that white or grey objects are truly white or grey and do not have a bias towards a particular color when, as we see here, the lighting changes. Depending on the camera, the white balancing can be performed in camera on the FPGA or ISP or on the host PC in software. And if using the software calculation, we have the option here to reduce processor overheads by skipping frames. If a neutral scene is not possible, a region of interest can be set in the scene on an area that is neutral, whilst the remaining image can contain colours. In this example, the non-neutral background is affecting the quality of the white balancing, and even though the white balance may look okay to the eye, with the line view tool we can see it is not optimum. By unlocking the white balance ROI control and then defining a new region of interest restricted to our neutral target, we're able to achieve an accurate white balance even with areas of colour in the scene. One thing to note is that the neutral area should not be overexposed, as this will affect the quality of the auto white balance calculation. So whilst white balancing ensures more accurate colours, black level is used to preserve detail in darker areas of the image. In some applications, it's important that the pixel value for true black in the image is not set to exactly 0, as this can clip information in the image if there are any subsequent decreases in the image brightness. If we increase the exposure time or the gain to compensate for this, we may see saturation in brighter areas of the image. By setting a black level offset, the grey levels of the dark areas are increased, but without significantly affecting the brighter pixels. With the pixel viewer in Peak Cockpit, we can see the pixel values for the darkest areas of the scene to help set the offset correctly. In the Brightness and Frame Rate tab in Peak Cockpit, we can set an offset on the black level so the pixel value is around 20 for an 8-bit image to ensure that all of the pixel information is available even if the image brightness changes. However, under some circumstances, this true black level may still shift, likely due to white balancing, adjusting the RGB gains on a color camera, the operating temperature of the camera changing, or possibly through a general change in the sensor performance over time. Therefore, by enabling the auto black level, The camera can dynamically adjust the true black level so that it remains constant over time and we achieve consistent results. The XC has a voice coil lens and the LEAF family has various liquid lens options, and these can be controlled to either manually position the focus or to use autofocus algorithms to automatically set the focus. With the XC, the process is quite simple as the autofocus processing is performed directly on the camera in the ISP, and there are no configuration options to consider other than the autofocus ROI, which we will come to. With the LEAF cameras, autofocus is performed in software on the host PC and therefore opens up the possibility for more configuration and optimization. Within Peak Cockpit, we can open the focus and image sharpness dialog, and we see the autofocus drop-down box. Here, by default, it is disabled, so only the focus setting slider is enabled, with which we can manually adjust the focus. Set autofocus to once or to continuous, and the search algorithm and sharpness calculations become active, and the focus setting slider is disabled, temporarily with a one-time process, or always if continuous mode is enabled. Autofocus involves two separate tasks. First, a sharpness metric measures how well focused the current image is, and second, a search algorithm changes the lens position to find the setting that produces the highest sharpness value. Here we can select the search algorithm and the sharpness algorithm. If we need speed, then a good start is to use the Teningrad sharpness method and the golden ratio search for the focus position. And if we need accuracy, we can start again with the Teningrad sharpness method, but with the full scan autofocus search. Some evaluation will likely be necessary to determine the best combination for the application. The specifics of each method used are beyond the scope of this video, but detail can be found in the Peak user manual, and as would be expected, different approaches balance speed and accuracy. We can optimize the autofocus speed by restricting the search range min and max if we know the focus range we should work in. We can skip frames so the autofocus is not calculated on every image, and we can also adjust the hysteresis value. Increasing the value will mean the search algorithm will settle on a focus position faster, but with lower accuracy. The autofocus region of interest limits the autofocus calculation to the part of the image that matters for the application. This prevents things like foreground objects from influencing the result. Here, we draw the region of interest around the target features, and the camera adjusts the focus specifically for that area. To summarize, IDS Peak provides a range of automatic image optimization features, including auto brightness, auto white balance, auto black level, and autofocus, and these can be evaluated and configured through Peak Cockpit. These functions can help simplify camera setup and maintain consistent image quality as lighting, color conditions, or object distance change. Depending on the camera, the processing may be performed directly on the camera or on the host PC with different levels of configuration available. The exact features supported depend on the camera model, and we can check the available functions for each camera on the relevant product pages on the IDS website.